Imagine looking up at the night sky and realizing that every star, every planet, and even our own Milky Way are part of an immense cosmic story, one written in violence and sculpted by gravity. Out there, in the profound silence of space, galaxies are not simply drifting alone. They collide, they merge, they tear each other apart in a slow, majestic ballet that has been unfolding for billions of years. It's a process so immense, so powerful, that it defies everyday understanding, yet it's through these very acts of destruction that new suns are ignited, new worlds assembled, and new galaxies born. These are tidal galaxies, structures forged in the gravitational turmoil of close encounters, where the pull between massive bodies stretches stars and gas into brilliant, sweeping arcs and luminous tails. What may look like chaos is, in truth, one of the universe's most creative engines. From the debris of shattered galaxies emerge stellar nurseries glowing with infant stars, and within the chaos, the seeds of future solar systems are sown. This is where endings and beginnings are woven together, revealing a truth far grander than we often grasp, that creation requires destruction, and that beauty in the cosmos is often born from violence. In this video, we'll journey deep into the heart of these spectacular encounters. We'll explore how tidal forces not only tear galaxies asunder, but also trigger the birth of stars and shape the evolution of cosmic structures on a scale almost beyond imagination. From understanding the role of dark matter in these interactions to previewing the ultimate fate of our own galaxy, we'll uncover how astronomers decode these magnificent events and what they teach us about the universe's past, its future, and our place within it. So join us as we unravel the story written in starlight and gravity, a story of chaos and creation that continues to transform the cosmos. So what exactly are these tidal galaxies we've been talking about? Think of them not as a single, distinct type of object, but rather as a phase in a galaxy's life, a dramatic and transformative one. They are the visible scars and brilliant aftermath of a close gravitational encounter. When two galaxies pass near each other, they don't simply bump and bounce away like billiard balls. Instead, their immense gravitational fields reach out and grip one another, pulling and stretching their constituent stars, gas clouds, and dust into long, luminous rivers that stream out into the intergalactic void. These are the tidal tails and streams, the defining features that give these systems their name. But to call them mere accidents of gravity would be to miss their true significance. These spectacular structures are, in effect, open books written in starlight. Each stream, each arc, tells a specific story about the encounter that created it, the masses of the galaxies involved, their angle of approach, their speed, and even their internal composition. Astronomers have learned to read this celestial handwriting. By carefully mapping the faint light of these tidal features, they can work backwards, effectively replaying the cosmic collision in sophisticated computer models to understand not just what happened, but why. This turns every tidal galaxy into a natural laboratory, one where the most fundamental forces of the universe are operating on a breathtaking scale. Within these laboratories, we can observe the direct consequences of gravitational violence. We see how gas clouds, once serene, are violently compressed, triggering firestorms of new star birth. We witness how the very architecture of a galaxy can be torn down and rebuilt into something new. It's a process that unfolds over hundreds of millions of years, a slow-motion ballet of destruction and renewal that ultimately drives the evolution of galaxies across cosmic time. By studying these beautiful wrecks, we are decoding the history of the universe itself, one gravitational encounter at a time. To grasp the immense power at work in these galactic encounters, we must first understand the master artist behind the scenes, gravity. It is the fundamental force that orchestrates the entire cosmos, an invisible hand that sculpts the universe on its grandest scales. Unlike the fleeting violence of an explosion, gravity operates with a patient, relentless pull, drawing massive objects together over incredible spans of time and space. It is this persistent attraction that sets the stage for the most dramatic events in the life of a galaxy. When two galaxies are drawn into each other's gravitational embrace, the resulting interaction is nothing short of a cosmic dance. They don't simply crash head-on like two cars. Instead, they swing past each other in a graceful, albeit destructive, arc. As they pass, their mutual gravitational pull acts like a tug of war on their very structures. The side of one galaxy closer to its partner feels a stronger pull than the far side, and this difference in force, what we call a tidal force, stretches and distorts the galaxies. Imagine gently pulling on a ball of cotton candy. It doesn't break cleanly, but instead pulls out long, wispy strands. In a galactic context, those strands are made of billions of stars, immense clouds of gas, and cosmic dust, all drawn out into spectacular, luminous tails that can stretch for hundreds of thousands of light years. But the story doesn't end with destruction. This gravitational chaos is also the catalyst for breathtaking creation. As those vast clouds of hydrogen gas are pulled, squeezed, and compressed by the tidal forces, they collapse under their own weight. Within these now dense regions, the temperature and pressure skyrocket until they reach a critical point, the birth of a star. What was once a peaceful, diffuse cloud is suddenly a brilliant stellar nursery, igniting thousands, even millions, of new suns in a wave of star formation. The very same force that tears the galaxies apart also provides the spark for new beginnings, demonstrating the universe's remarkable cycle of death and rebirth. This delicate balance, where destruction directly fuels creation, is one of gravity's most profound and beautiful lessons. While the immense dance of colliding galaxies has likely occurred for billions of years, our ability to see and understand it is a surprisingly recent chapter in astronomy. For centuries, telescopes simply weren't powerful enough to discern the faint, ghostly tendrils of stars that are the telltale signs of these encounters. These delicate tidal features are incredibly diffuse, often lost in the glare of their parent galaxy's bright cores. The true story of their discovery begins with the arrival of truly massive observatories and the photographic plate, which could patiently collect light over long exposures to reveal what the human eye could not see in a fleeting glance. It was the great astronomer Edwin Hubble, working with the then revolutionary 100-inch Hooker telescope at Mount Wilson in the early 20th century, who first systematically catalogued these strange celestial objects. He noticed that some galaxies, which he called peculiar nebulae, had bizarre, irregular shapes, odd wisps, extensions, and bridges of light that defied the simple classifications of spiral or elliptical. He even observed the system we now know as the antennae galaxies, noting its peculiar curved tails, but the technology of his time could not definitively answer how such structures formed. The prevailing view was that galaxies were largely isolated island universes, and these features were curious anomalies rather than evidence of profound interactions. The paradigm shift didn't occur until the latter half of the 20th century. Two key advancements converged to crack the code. First, new, larger telescopes, and crucially, the advent of sensitive electronic detectors like CCDs, which replaced photographic plates, finally provided the clarity and light-gathering power needed to study these faint tidal streams in detail. Astronomers could now see that these arcs and tails were not just random blobs but coherent structures made of countless individual stars. Second, and perhaps just as importantly, was the rise of computational power. For the first time, scientists could create sophisticated simulations that modeled the laws of gravity on a galactic scale. They could digitally recreate two galaxies passing by one another and watch, over millions of simulated years, as the exact same tidal tails and bridges emerged from the calculations. The virtual collisions matched the real-world observations perfectly. This was a monumental revelation. It proved that these peculiar galaxies were not oddities but snapshots of a universal and common process. The faint streams of stars were the direct evidence, the forensic proof, of a past gravitational encounter. This realization completely overturned our understanding of galaxy evolution. We moved from a static view of the universe where galaxies lived in isolation to a dynamic one where collisions and mergers are fundamental engines of change. These historical discoveries showed us that the universe is a constantly evolving, often violent, and deeply interconnected place, where a galaxy's present shape is a testament to its past interactions. This brings us to one of the most breathtaking revelations from the study of these galactic collisions: the profound and direct link between utter chaos and the birth of new stars. It seems counterintuitive, this idea that violence on such an unimaginable scale could be the very cradle of creation. Yet, within the swirling maelstrom of a galactic encounter, that is precisely what occurs. The key player in this transformative process is the immense reservoir of interstellar gas that permeates every galaxy. In a quiet, isolated spiral, this gas is often too diffuse and too calm to collapse under its own weight. It simply exists as a vast, cold cloud drifting peacefully between the stars. But when a tidal encounter begins, this serene environment is thrown into turmoil. As the gravitational tides pull and stretch the galaxies, they don't just affect the stars, they act with immense force on these clouds of gas and dust. Think of it like squeezing a handful of snow to form a compact snowball. The tidal forces violently compress these gaseous clouds, pushing them together, increasing their density to incredible levels. This compression is the crucial trigger. It raises the internal pressure and temperature of the gas to a point where its own gravity can no longer be resisted. The cloud begins to collapse inward upon itself, fragmenting into dense, hot cores, and within these cores the magic happens. As gravity takes over completely, pulling every atom toward the center, the temperature soars into the millions of degrees. At this critical juncture, the furnace of nuclear fusion ignites and a new star is born. What's truly spectacular is that this isn't a solitary event. The tidal forces compress gas across vast regions of the interacting galaxies, leading to a veritable firestorm of star formation, what astronomers call a starburst. We can actually see this brilliant evidence in the brightest knots of light that stud the long, flowing tidal tails. Those are not random clumps of stars, they are massive clusters, stellar nurseries glowing with the intense blue light of countless hot, young, newborn stars. This is creation on an epic scale, all sparked by the destructive gravitational pull of a galactic neighbor. It's a powerful cosmic lesson that from the ashes of the old, something new and magnificent can always emerge. To see these principles in action, we need look no further than a spectacular pair of galaxies known as NGC 4676, more famously called the Mice. Located about 300 million light-years away in the constellation Coma Berenices, these two spiral galaxies are currently in the midst of a breathtakingly slow and graceful collision, caught by our telescopes in what is essentially the opening act of their merger. Their name comes from the two incredibly long, thin tidal tails that stream out behind them, resembling the tails of two mice scurrying away from each other. But these are no simple trails of light. They are dynamic, evolving structures that tell a vivid story of gravitational violence and stellar creation. What makes the mice such a perfect laboratory is their stage in the collision process. They are not yet fully merged, nor are they just beginning their interaction. They have already made their first close pass, and the gravitational tides have done their work, pulling vast amounts of material out of each galaxy's disk. The Hubble Space Telescope, with its unparalleled resolution, has provided us with an incredibly detailed portrait of this system. In its images, we can see far more than just the two bright cores and their sweeping tails. We can resolve individual clusters of brilliant blue stars lighting up within those tails like strings of cosmic pearls. That distinctive blue hue is the unmistakable signature of hot, massive, young stars that were not there before the galaxies began their dance. They are the direct result of the violent compression of gas clouds during the encounter, a stunning confirmation of how tidal forces trigger epic waves of star formation. But the creation doesn't stop with stars. This violent redistribution of material is also the first step in building new worlds. As gas and dust are churned and mixed within the tidal tails and the galaxy's distorted disks, they provide the raw ingredients for planet formation. Within those dense, enriched clouds of material, microscopic dust grains can begin to clump together, eventually forming planetesimals and potentially full-fledged planetary systems. It's a profound thought. The same chaotic process that is tearing these galaxies apart is also sowing the seeds for new solar systems, some of which might one day host planets orbiting within the habitable zones of their newborn suns. The fate of the mice galaxies is also a preview of a distant future closer to home. Their interaction mirrors what will happen when our own Milky Way galaxy eventually collides with its massive neighbor, the Andromeda galaxy. While that event is billions of years away, studying systems like the mice allows astronomers to model and predict the stages of that future collision with remarkable accuracy. We can see in real time elsewhere in the universe how such an encounter will likely stretch our galaxy, trigger a firestorm of new star birth, and ultimately reshape both systems into something new. The mice offer us a cosmic crystal ball, showing that even the most colossal structures in the universe are not permanent, but are constantly evolving through processes of magnificent destruction and renewal. While the birth of new stars is a spectacular outcome of galactic encounters, there is another, even more transformative process at work in these interactions, one that reveals a darker, more competitive side of cosmic evolution. This brings us to our second key insight, the phenomenon of galactic cannibalism. It's a term that perfectly captures the visceral reality of what happens when the gravitational dance between galaxies is not a meeting of equals, but rather a predatory encounter. In the vast expanses of space, larger, more massive galaxies often consume their smaller, weaker neighbors, absorbing them entirely in a process that fundamentally alters both the predator and the prey. We can see evidence of this cosmic consumption happening right in our own cosmic backyard. Our nearest large galactic neighbor, the Andromeda galaxy, is a classic example of a cannibal. Surrounding it, astronomers have discovered vast, faint streams of stars' tidal streams that trace elegant, looping arcs across the sky. These are not random collections of stars. They are the dissolving remains of smaller dwarf galaxies that Andromeda has gravitationally captured, torn apart, and is in the process of assimilating. Each stream is a fossilized record of a past meal, a ghostly testament to a smaller galaxy that was pulled in by Andromeda's immense gravity, stretched into a long ribbon by tidal forces, and then slowly digested over billions of years, its stars becoming a permanent part of the larger galaxy's halo. This process of growth through consumption is a primary driver of galactic evolution. A large spiral galaxy like our Milky Way didn't simply form its majestic spiral arms and vast halo of dark matter in isolation. It has grown to its current size and shape by repeatedly absorbing smaller satellite galaxies throughout its long history. Each act of cannibalism provides a fresh infusion of raw material stars, but more importantly, vast quantities of cool gas. This newly acquired gas is the lifeblood for future generations of stars, sinking toward the galactic disk and providing the fuel for new rounds of star formation. The cannibal galaxy doesn't just get bigger, it gets reinvigorated, its development fueled by the very substance of its vanquished neighbors. This violent method of growth also helps explain the incredible diversity of galaxies we observe across the universe. The largest and most massive galaxies we see, the giant ellipticals that sit at the hearts of dense galaxy clusters, are likely the product of not just one, but many such cannibalistic mergers over cosmic time. They are the ultimate cosmic predators, having consumed countless smaller galaxies to achieve their enormous size and smooth, featureless shape. This establishes a clear hierarchy in the cosmos, a food chain where gravity is the ultimate arbiter. The growth and evolution of a galaxy are therefore not a gentle process of quiet accumulation, but a dynamic and often violent history of encounters, a story of survival, consumption, and transformation written in the stars themselves. So far, we've seen how the violent ballet of colliding galaxies sculpts beautiful streams of stars and ignites stellar nurseries. But there's an invisible partner in this dance, one that holds the entire performance together: dark matter. Every galaxy, including our own, is thought to be embedded within a vast spherical halo of this mysterious substance. Unlike stars and gas, dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. We only know it's there because of its profound gravitational influence on the things we can see. It's the hidden scaffolding upon which the visible universe is built. When two galaxies interact, their visible stars and gas are pulled into those spectacular tidal tails, but their dark matter halos interact as well, and in ways that are far more difficult to observe. Sophisticated computer simulations of these cosmic collisions reveal something fascinating. As the galaxies swing past each other, their dark matter halos can be gravitationally stripped, with some of the dark matter pulled away into the intergalactic void. In other cases, the halos can become significantly distorted, their perfect spherical shapes warped by the gravitational tug of war. This has a direct and crucial impact on the visible galaxy we see. The dark matter halo provides the majority of the gravitational glue that holds a galaxy together. If that halo is altered or stripped away during a collision, it can change the very binding energy of the stars and gas, influencing how much material is ultimately lost to tidal tails and even determining the long-term fate of the galaxy after the encounter. This presents astronomers with a unique and powerful opportunity. Because we cannot see dark matter directly, we have to map its presence indirectly by studying its gravitational effects on visible matter. Tidal features are like nature's own dark matter detectors. The precise shape, length, and density of the streams of stars are dictated by the gravitational forces at play, forces dominated by the distribution of dark matter. By meticulously measuring the geometry of these tidal tails and then comparing those observations to supercomputer simulations, scientists can work backwards to infer the properties of the invisible dark matter halos involved. They can ask what kind of dark matter distribution, with what mass and what shape, would create the exact tidal features we see in a system like the mice galaxies or the antennae. This method allows them to create a gravitational map, charting the unseen dark matter that governs the interaction. In this way, the violent and beautiful chaos of galactic collisions becomes one of our most valuable tools for probing the nature of dark matter itself. The way dark matter behaves during these encounters, whether it clumps more or less than visible matter, how easily it is stripped, how it responds to gravitational forces, provides critical clues that could help distinguish between different theoretical models of what this mysterious substance actually is. By studying the visible wreckage of these cosmic crashes, we are ultimately illuminating the invisible, bridging the gap between the world we see and the hidden mass that shapes it, bringing us one step closer to solving one of the greatest mysteries in all of modern physics. Beyond simply triggering waves of star formation or fueling galactic cannibalism, these gravitational encounters possess the power to completely reinvent a galaxy's fundamental architecture. This is our third key insight. Tidal forces are master sculptors capable of reshaping a galaxy's very morphology, its form and structure, transforming it from one recognized type into something entirely different. We often picture galaxies as static, timeless portraits, elegant spirals with their pinwheeling arms, or smooth, featureless ellipticals like cosmic eggs. But this is a snapshot view. The reality is that galaxies are dynamic entities, and their shapes are not permanent. They are fluid, changing over billions of years, and the primary catalyst for that change is a violent gravitational encounter. Perhaps the most stunning example of this creative destruction is the Cartwheel galaxy. Located about 500 million light-years away, this object looks like nothing else in the cosmos, a perfect bullseye with a bright central core, a shimmering ring of young stars, and a gossamer outer ring connecting it all. For a long time, its bizarre structure was a profound mystery. How could nature produce such a perfectly ringed galaxy? The answer, we now know, is a high-speed collision. Astronomers believe that several hundred million years ago, a smaller galaxy shot straight through the heart of what was then a normal spiral galaxy, much like a bullet passing through the center of a target. The gravitational shockwave from this direct hit radiated outwards through the galaxy's disk. This wave did not destroy the galaxy. Instead, it compressed the vast reservoirs of gas and dust orbiting the center, triggering a colossal wave of star formation that propagated outward, leaving in its wake the brilliant blue ring of newborn stars we see today. The Cartwheel galaxy is not an oddity. It is a masterpiece, a new galactic form forged in the fire of a collision. This process of morphological transformation explains one of the long-standing mysteries in astronomy, the origin of giant elliptical galaxies. These massive, roundish collections of old red stars are some of the largest galaxies in the universe. For decades, their formation was puzzling. The prevailing theory now, strongly supported by both observations and simulations, is that they are the end products of major mergers. When two spiral galaxies of roughly equal size collide and finally merge, the violent gravitational forces completely disrupt their delicate ordered structures. The beautiful spiral arms are shredded, and the orbital paths of billions of stars are randomized, creating a chaotic but gravitationally bound system. The gas from both galaxies is either rapidly consumed in a final starburst or ejected entirely, leaving behind a galaxy devoid of the raw material needed to form new stars or maintain a disk. What remains is a smooth, featureless elliptical galaxy, a completely new entity born from the total demolition of its progenitors. This revelation fundamentally changed our understanding of galactic evolution, showing that a galaxy's type is not a fixed identity, but a temporary phase in its long and eventful life, a phase entirely subject to change by the transformative power of cosmic violence. While we can observe the magnificent results of these galactic collisions through our most powerful telescopes, there's a fundamental limitation to our view. we are only ever seeing a single, frozen moment in a process that unfolds over hundreds of millions of years. It's like walking into a movie theater and seeing only one frame from the entire film. You can see the drama, but you have no way of knowing how the story began or how it will ultimately end. This is where the true power of advanced computer simulations comes into play, serving as a time machine that allows astronomers to rewind and fast-forward these cosmic encounters, unlocking their secrets in a way pure observation never could. These aren't simple video game graphics, they are some of the most complex and computationally intensive models ever created, running on the world's most powerful supercomputers. Programs with names like Illustris, Eagle, and Aripo are in essence entire virtual universes built from the fundamental laws of physics. Scientists input equations for gravity, hydrodynamics, thermodynamics, and even the complex chemistry of interstellar gas. They then set up the initial conditions, perhaps two spiral galaxies on a collision course, and let the simulation run. For weeks or even months, the supercomputer crunches quintillions of calculations, modeling how every particle of dark matter, every star, and every cloud of gas will interact over cosmic time. The goal is breathtakingly ambitious: to see if the virtual universe behaves like our real one, and the results have been nothing short of revolutionary. When astronomers point these simulations at a famous system like the Antennae galaxies, they can input the estimated masses, speeds, and angles of approach, press play, and watch as their digital creation perfectly replicates the real-world tidal tails, the bursts of star formation, and the overall morphology of the collision. This is the ultimate test of a scientific theory, not just explaining what we see, but accurately predicting it. When the simulation's final product matches a Hubble image with stunning precision, it gives us tremendous confidence that our understanding of the underlying physics of gravity, dark matter, and gas dynamics is fundamentally correct. But these virtual telescopes do far more than just recreate what we already know. They allow scientists to conduct experiments that are impossible in the real world. What would happen if the collision angle was slightly different? What if one galaxy had more dark matter? What is the precise role of magnetic fields in shaping the tidal tails? In a simulation, an astronomer can tweak a single variable and run the experiment again, isolating its effect on the outcome. This has provided profound insights that observations alone could never have revealed, such as the intricate way dark matter halos are stripped during a merger, or how supermassive black holes at the centers of galaxies are awakened by the influx of gas from a collision. By extending our vision into realms of time and scale that are otherwise inaccessible, computer simulations have become an indispensable partner to our telescopes, working in tandem to write the definitive story of how violence and gravity shape the evolving universe. Now consider one of the most fascinating and counterintuitive outcomes of these galactic collisions: the birth of entirely new galaxies from the wreckage of the old. We've seen how tidal forces can tear galaxies apart, but in that very process of destruction, they can also assemble something new and independent. Within the long, flowing rivers of stars and gas that stream out into intergalactic space, something remarkable can happen. Dense clumps of material, rich with hydrogen gas and dust, can become gravitationally bound to themselves. They are no longer just debris being pulled away. They become their own distinct, self-gravitating entities. These are tidal dwarf galaxies, and their existence turns our traditional understanding of galaxy formation on its head. For a long time, the dominant cosmological model held that galaxies formed in a top-down manner. Vast halos of dark matter would collapse first, their immense gravity then drawing in the gas that would eventually cool and fragment to form stars, building a galaxy from the inside out. The smallest galaxies were thought to be the oldest, the first fragments to condense after the Big Bang. Tidal dwarf galaxies shatter this neat hierarchy. They are not ancient relics, they are cosmic newborns, formed within the last few 100 million years from the recycled material of their parent galaxies. They are built not from pristine primordial gas, but from the enriched debris of previous generations of stars, a second or even third generation of galactic formation. A spectacular example of this process can be witnessed in the Tadpole galaxy. This famously distorted system, with its enormous tail stretching across 280,000 light-years of space, is the result of a recent disruptive encounter with a smaller intruder galaxy. That colossal tail is not a smooth stream. Hubble Space Telescope observations reveal it is studded with brilliant blue knots. These are not just clusters of stars. At least two of the largest knots have been confirmed as tidal dwarf galaxies in the making. They contain not only millions of young, hot stars, but also significant reservoirs of the gas and dust required to form even more stars and planetary systems in the future. They are, in every sense, fledgling galaxies being spun out of the turmoil of a collision, demonstrating that galaxy birth isn't confined to the early universe, but is an ongoing, dynamic process. Studying these unique objects provides astronomers with a powerful laboratory to understand the fundamental recipe for building a galaxy. Because they are born from the collisional debris of larger galaxies, tidal dwarfs are expected to have a crucial difference from their primordial cousins. They should contain very little, if any, dark matter. In the standard model of galaxy formation, dark matter is the essential ingredient, the gravitational foundation upon which everything else is built. But in a tidal interaction, the dark matter halo, which is more diffuse and spread out, is less likely to be pulled into the same dense, gas-rich knots as the visible matter. Therefore, if a tidal dwarf galaxy can form, stabilize, and persist, it proves that a massive dark matter halo is not an absolute requirement for galaxy formation. This makes them critical test cases for our theories of gravity and structure formation. By measuring their masses and motions, scientists can probe whether the laws of physics operate differently on the scale of these tiny, dark matter-free galaxies, offering potential insights into alternative theories like modified Newtonian dynamics. In this way, these tiny galaxies born from violence are challenging our most fundamental assumptions about how the universe builds its largest structures. But the influence of these titanic collisions reaches far beyond the visible stars and gas, probing deep into the very heart of a galaxy, where a different kind of monster lies in wait. At the center of nearly every large galaxy, including our own Milky Way, resides a supermassive black hole, an object so dense that not even light can escape its gravitational grip. For much of a galaxy's life, these black holes may lie dormant, quiet giants sleeping in the dark. However, the violent turmoil of a galactic encounter can be the very thing that stirs them awake, with spectacular and far-reaching consequences. The mechanism is both elegant and destructive. As the gravitational tides of a collision churn a galaxy's structure, they don't just pull material out into tidal tails. They also push enormous quantities of gas and dust inward on a direct collision course with the galactic center. Think of it like a river suddenly changing course, its waters funneled into a narrow canyon. Vast clouds of interstellar gas, which might have peacefully orbited for billions of years, are now driven relentlessly toward the waiting black hole. This gas doesn't fall in directly. Instead, it forms a swirling, superheated disk of material, an accretion disk, that spirals around the black hole at nearly the speed of light. Friction within this disk heats it to temperatures of millions of degrees, causing it to glow with incredible brilliance across the entire electromagnetic spectrum, from radio waves to gamma rays. When this happens, the galaxy's core is transformed into what astronomers call an active galactic nucleus, or AN. It becomes one of the most powerful and energetic engines in the universe, capable of outshining all the billions of stars in its host galaxy combined. The awakening of an AGN is not a gentle process, it is a cosmic cataclysm. The black hole doesn't just consume this incoming material, it also channels some of the immense gravitational energy into launching twin jets of charged particles that scream out into intergalactic space at nearly the speed of light, often stretching for thousands or even millions of light years. These jets can carry away phenomenal amounts of energy, and where they slam into the tenuous gas between galaxies, they create colossal, glowing lobes that are visible to radio telescopes. This profound connection between external violence and internal awakening is perfectly illustrated by a famous galactic neighbor, NGC 5128, better known as Centaurus A. Even a casual glance at an image of this galaxy reveals a universe of chaos. It presents a bizarre mix of a dusty, warped disk that looks like it was roughly stitched onto a giant elliptical galaxy. Cutting across it all are dramatic dark lanes of obscuring dust, the telltale signs of a past merger where a smaller spiral galaxy was consumed. These are the clear tidal features of a violent history. But that's only half the story. Centaurus also possesses one of the closest and most powerful active galactic nuclei to Earth. Its supermassive black hole is actively feeding, blasting out immense radio jets that extend far beyond the visible galaxy. This makes it an undeniable case study. The same colossal collision that distorted its visible shape also funneled fuel to the central black hole, igniting its brilliant engine. The impact of this activity on the host galaxy is profound and complex. The enormous energy released by an AGN can have two seemingly opposite effects on star formation. Initially, the intense radiation and powerful outflows can blast away remaining gas reservoirs or heat them to such high temperatures that they cannot collapse to form new stars. This is a form of negative feedback, effectively quenching star formation and potentially leading to the galaxy's aging and reddening. However, in other scenarios, the shock waves from these outflows can also compress distant clouds of gas at the galaxy's outskirts, triggering new rounds of star formation in a positive feedback loop. This intricate dance demonstrates that a galactic collision doesn't just reshape a galaxy from the outside in. It also transforms it from the inside out, linking the vast scale of gravitational encounters to the furious activity at the very heart of darkness, and showing that every part of a galaxy is deeply interconnected in the cycle of violence and creation. This brings us to a fifth, and perhaps most personal, insight drawn from the study of these cosmic collisions: the profound role they play in seeding the universe with the very building blocks of life itself. We are, each of us, made of stardust, a poetic phrase that holds a deep scientific truth. The atoms that constitute our bodies, the iron in our blood, the calcium in our bones, and the oxygen we breathe, were all forged in the nuclear furnaces of ancient stars and then blasted across space in the violent explosions of supernova. For billions of years, these heavy elements, which astronomers call metals, remained scattered and isolated within the individual galaxies where they were created. But galactic collisions act as the universe's ultimate recycling plants, gathering these disparate materials and mixing them together on a colossal scale, a process known as chemical enrichment. When two galaxies merge, it is not a clean or gentle process. It is a chaotic, turbulent mixing of their entire interstellar mediums, the vast clouds of gas and dust that float between the stars. Imagine two different colors of paint being violently swirled together with a palette knife. They don't stay separate but instead create a new, blended hue. In a galactic merger, the enriched gas from one galaxy, which may be rich in silicon or carbon from its own history of stellar death, is churned together with the gas from its partner, which might have a different chemical signature. This creates a new, homogenized interstellar soup that is far more chemically diverse and rich than what existed in either galaxy before the collision. We can actually observe this enrichment happening in the tidal streams themselves, where spectroscopic analysis reveals the distinct chemical fingerprints of elements spread far from their original stellar nurseries. This cosmic recycling has a direct and incredible consequence. It dramatically increases the potential for the formation of rocky planets and, by extension, the possibility of life. The very first stars in the universe, known as population 3 stars, were composed almost entirely of hydrogen and helium. When they died, they released the first heavy elements into the cosmos, but those elements were scarce and unevenly distributed. For a planet like Earth to form, you need an abundance of elements like iron, nickel, silicon, and oxygen to create a solid core and mantle. You need carbon for organic chemistry. Without galactic collisions to stir the pot and mix these elements thoroughly back into the raw material for new stars, later generations of stars might have formed in relatively pristine, metal-poor environments, perhaps only yielding gaseous planets like Jupiter. The violence of these encounters ensures that the valuable ashes of dead stars are not wasted, but are instead incorporated into the next generation of star-forming regions. Therefore, the planetary systems that coalesce from the enriched clouds within post-collision galaxies, or even within the tidal dwarfs we discussed, start with a much richer and more diverse set of ingredients. This doesn't just make rocky planets more likely, it also increases the chemical complexity available on those planets' surfaces. The same cosmic violence that tears galaxies apart is, in a very real sense, responsible for dispersing the essential elements that can one day form oceans, atmospheres, and perhaps even the complex molecules that lead to biology. It's a humbling and awe-inspiring connection. The catastrophic events we witness on the grandest of scales are directly linked to the possibility of life on worlds orbiting distant suns, underscoring the idea that destruction and creation are not just linked, but are essential partners in the universe's ongoing story of innovation and complexity. To truly decipher the story written in the tidal streams of galaxies, astronomers must act as cosmic detectives, employing a diverse toolkit of observational instruments. Each tool reveals a different piece of the puzzle, allowing scientists to see not just the visible aftermath of a collision, but the underlying processes that drive it. The most iconic views come from large optical telescopes, both on the ground and in space. Instruments like the Hubble Space Telescope have provided us with those breathtaking, high-resolution portraits that capture the intricate architecture of tidal tails and bridges in stunning detail. By observing invisible light, these telescopes map the distribution of stars, revealing the sheer scale of the gravitational disruption and pinpointing the brilliant blue knots of recent star formation. But starlight only tells part of the story. To understand the full narrative, astronomers must also trace the vast reservoirs of cold hydrogen gas, the primary fuel for future stars, that are often invisible to optical eyes. This is where radio telescopes, like the legendary Arecibo Observatory or the powerful Very Large Array, come into play. These immense instruments detect the faint radio waves emitted by neutral hydrogen atoms. By mapping this emission, they can chart the distribution and motion of gas within and around interacting galaxies, often revealing that the tidal features seen in starlight are just the tip of the iceberg. Enormous streams of gas stripped from the galaxies during their encounter can extend far beyond the visible starlight, showing the true extent of the gravitational damage and highlighting the raw materials available for future cosmic construction projects. The quest for a complete understanding doesn't stop there. Space-based observatories working outside the blurring effect of Earth's atmosphere provide critical data across other wavelengths. The Spitzer Space Telescope, for instance, observed the universe in infrared light, allowing it to peer through obscuring clouds of dust to see star formation occurring hidden from view. The Chandra X-ray Observatory detects high-energy X-rays, revealing the presence of superheated gas and the violent activity of supermassive black holes that are often awakened by the influx of material from a collision. Each wavelength, from radio to gamma rays, adds a new layer of information, a new color to the picture, transforming a two-dimensional snapshot into a multi-dimensional understanding of the physics at work. Perhaps the most transformative advancement has been the rise of massive, automated sky surveys. Projects like the Sloan Digital Sky Survey have methodically scanned huge portions of the heavens, not to study one specific object, but to catalog everything in its path. This wide-net approach has been invaluable for tidal galaxy research because it has revealed that these interactions are far more common than we once thought. By algorithmically scanning through images of millions of galaxies, astronomers have been able to identify thousands of systems showing signs of tidal disturbances, faint shells, delicate loops, and warped disks that might have been missed in targeted studies. This vast statistical sample allows scientists to move beyond individual case studies and understand the broader role mergers play in the life cycle of galaxies across cosmic time. Finally, the data from all these sources, optical, radio, infrared, and X-ray, is fed into the sophisticated computer simulations we discussed earlier. The simulations act as a crucible where theory and observation meet. Astronomers can tweak the initial conditions of a virtual collision to see which set of parameters produces a result that matches the multi-wavelength data from a real-world system like the antennae galaxies. This iterative process of observing, simulating, comparing, and refining is how we piece together the full history of these encounters. It allows us to determine not just what we are seeing, but how it happened, how long it took, and what the galaxies involved will ultimately become. This synergy of technology and theory is what transforms faint smudges of light into a profound understanding of the violent, creative forces that continue to shape our universe. While we've been exploring these magnificent collisions in the far reaches of the cosmos, it turns out we are not merely distant observers of this grand cosmic drama. We are, in fact, future participants. The same violent and creative processes that have shaped galaxies across the universe are written into the destiny of our own celestial home. The Milky Way, the majestic spiral we are a part of, is not traveling through space in serene isolation. It is part of a local gravitational family, the local group, and it is on an inescapable collision course with its largest neighbor, the Andromeda galaxy. This isn't a speculative possibility. It is a firm prediction based on decades of precise measurements of the motions of both galaxies. They are currently hurtling towards each other at a breathtaking speed of about 110 kilometers per second. But given the immense distances involved, this cosmic crash is still a very long way off, set to begin in earnest in about 4 to 5 billion years. When that encounter finally commences, it will unfold as a spectacular, slow-motion ballet lasting billions of years, perfectly mirroring the interactions we've studied in systems like the mice galaxies. The first close pass will be a gravitational spectacle. The mutual tidal forces will warp and distort the beautiful spiral structures of both the Milky Way and Andromeda. Vast rivers of stars, gas, and dust will be pulled out from their disks, creating brilliant, luminous tidal tails that stretch across the heavens. From the perspective of any future inhabitants of Earth, the night sky would transform into a breathtaking canvas of cosmic chaos, with the once faint smudge of Andromeda swelling to dominate the entire view before the gravitational dance begins to tear both galaxies apart. Yet, just as we've seen elsewhere, this destruction will be the precursor to an epic act of creation. The violent compression of the immense gas clouds within both galaxies will ignite a firestorm of new star formation, likely the most prolific burst of stellar birth in the entire history of either galaxy. The sky would be filled with the light of countless new suns flaring to life. But this stellar baby boom will also be relatively short-lived, as the vast reservoirs of star-forming gas are either rapidly consumed in this brilliant starburst or blown away by the powerful outflows from newly awakened supermassive black holes at the centers of both galaxies. The gravitational tug-of-war will not end with that first pass. The two galaxies, now locked in a tight orbital embrace, will swing past each other again and again, each encounter further erasing their original identities. Their structures will be completely randomized, their spiral arms shredded into oblivion. After perhaps a billion years of this dance, they will finally merge completely, ceasing to be two distinct spirals and coalescing into a single new type of galaxy, a giant elliptical. Astronomers have playfully dubbed this future hybrid galaxy Miltromda or Milcomda. This new entity will be a smooth, featureless collection of stars, largely devoid of the cool gas needed to form new suns and populated mostly by older, redder stars. The familiar Milky Way as we know it will be gone, but its stars, along with those of Andromeda, will live on as part of this new, larger cosmic island. This profound prediction transforms our understanding of our place in the universe. It moves us from being simple spectators to being part of the ongoing narrative of cosmic evolution. The processes we study in distant tidal galaxies are not abstract events happening to others. They are a preview of our own long-term future. By meticulously observing and modeling collisions happening millions of light years away, we are effectively running a simulation of what will happen right here in our own neighborhood. This connection provides an incredible sense of context, emphasizing that galaxies are not permanent, static structures but dynamic entities with life cycles of birth, growth, and transformation. Our own galaxy's story is still being written, and its most dramatic, violent, and creative chapter is yet to come. While the grand-scale drama of colliding galaxies reshapes entire constellations of stars, the effects of this cosmic violence ripple down to a much more intimate level, the individual planetary systems orbiting within them. We often think of a star and its planets as a stable, almost sacred unit, a solar family peacefully orbiting for billions of years. But when a galaxy experiences a close gravitational encounter, that perceived stability can be shattered. The immense tidal forces that pull entire galaxies out of shape also exert a powerful, and often disruptive, influence on the delicate orbital dances of planets around their host stars. Imagine a star system peacefully orbiting the outer reaches of a spiral galaxy. As its host galaxy swings past another during a collision, the star experiences a sudden and profound change in the gravitational landscape. It's not a smooth, constant pull, it's a violent and shifting tug of war. This gravitational shockwave can profoundly destabilize the orbits of planets within that system. Some planets might have their orbits merely altered, becoming more elliptical or tilted. But in more extreme cases, a planet can be flung entirely out of its solar system, ejected into the frigid, dark emptiness of interstellar space to become a rogue planet, a forever wanderer without a sun. This is a fate of ultimate isolation, a world condemned to an eternal deep freeze, its potential for life extinguished by the gravitational turmoil of a galactic encounter. Yet, in a stunning demonstration of the universe's dual nature, the very same process that ejects planets into the void also creates the ideal conditions to forge brand new ones. This is where the concept of chemical enrichment becomes critically important on a planetary scale. As two galaxies merge, they don't just mix their gas, they churn together the enriched remains of countless supernovae from both systems, a cosmic cocktail now brimming with heavy elements like carbon, silicon, iron, and oxygen. This newly enriched material, compressed by tidal forces into dense pockets within tidal tails or in the central regions of the merging galaxies, becomes the prime raw material for a new generation of stars. And where new stars form, so too do new planetary systems. These second-generation planetary systems start with a tremendous advantage. They are born from a cloud that is already pre-loaded with a rich abundance of the essential ingredients needed to form rocky, terrestrial planets. This isn't just pristine hydrogen and helium. It's a pre-mixed blend containing all the elements required for a diverse array of worlds. This means the planets that coalesce around these new stars have a higher likelihood of being rocky bodies like Earth, rather than just gas giants. Furthermore, the increased metallicity, the abundance of elements heavier than hydrogen and helium, might also lead to a greater diversity of planetary types and sizes, potentially creating worlds with unique geological compositions and atmospheres that would be less common in more metal-poor, quieter regions of the universe. This has a profound implication for the search for life beyond Earth. The habitable zone, that Goldilocks region around a star where temperatures are just right for liquid water to exist on a planet's surface, is a key focus for astrobiologists. Galactic collisions, by both disrupting existing systems and seeding the formation of new ones in enriched environments, could actually increase the number of planets that end up in these life-friendly orbits within their new solar systems. While the violence of a merger might doom some worlds, it simultaneously sows the seeds for countless others, potentially increasing the overall statistical probability of life-bearing planets across the cosmos. This suggests that the most active, violent periods in a galaxy's history, epochs of frequent collisions, might not be barren wastelands but could instead be cosmic nurseries for planetary diversity, including worlds with the right conditions for biology to arise. It adds a fascinating and complex layer to our search for extraterrestrial habitats, suggesting that we may need to look not only to quiet, stable regions, but also to the dynamic, chaotic aftermath of galactic encounters to find the full spectrum of possibilities for life in the universe. This brings us to a profound shift in perspective, one that challenges our very perception of time and change in the universe. We've been discussing these galactic collisions as dramatic, violent events, which they are. But to our human senses, attuned to lifetimes measured in decades, the timescales involved are almost incomprehensible. A single galactic merger is not a sudden crash but a drawn-out ballet, unfolding over hundreds of millions, even billions of years. From our fleeting vantage point, these cosmic encounters appear to be frozen in time, beautiful but static snapshots. We are like mayflies trying to comprehend the slow growth of a redwood tree. Our entire existence is but a blink in the midst of this majestic, slow-motion drama. Yet, within the grand narrative of the cosmos, these events are not slow at all. In fact, they are remarkably rapid and efficient engines of change. Consider the entire 13.8 billion-year history of the universe as a single 24-hour day. On this cosmic clock, the formation of the first stars and galaxies takes up the entire morning and afternoon. Our own solar system forms sometime around the early evening. The entire reign of the dinosaurs, a period of over 160 million years that feels impossibly long to us, spans just about the last hour of this day. In this context, a galactic merger that takes 500 million years to complete is a transformation that happens in less than 90 minutes. It is a brief, intense, and transformative episode that can completely redefine a galaxy's structure, star formation rate, and ultimate destiny in what amounts to a cosmic instant. This duality of timescales, glacially slow to us, blisteringly fast to the universe, helps resolve what might seem like a paradox. How can the universe, which operates on such vast clocks, produce such dynamic and evolving structures? The answer lies in these concentrated bursts of activity. A galaxy might spend billions of years in a state of quiet, steady evolution, its stars peacefully cycling through their lives. Then, a close encounter with a neighbor acts as a powerful catalyst, compressing billions of years of potential change into a relatively short, violent period of intense creativity and destruction. It's a stellar baby boom followed by a period of quenching, a rapid morphological shift from spiral to elliptical, a sudden feeding of a central black hole, all of it happening in a mere fraction of the galaxy's total lifespan. These brief episodes of violence are the punctuation marks in the story of a galaxy's life, the decisive moments that set its course for the eons that follow. This understanding also reframes our own place in the cosmic story. When we look at an image of the antennae galaxies from the Hubble Space Telescope, we are not looking at a past event that is long over. We are witnessing a single frame from a movie that is still playing out. The light that reaches our eyes today left those galaxies hundreds of millions of years ago, and in the time it has taken that light to travel to us, the collision has progressed immensely. The stars we see being born in those bright blue knots have themselves lived, died, and perhaps seeded their surroundings with new elements. The merger may be nearing its completion, or the galaxies may have already fully coalesced into a new entity. Our view is not of the past, it is a deeply delayed transmission. This time lag is not a limitation but a gift, allowing us to study different stages of the same process by looking at different galaxies at various distances. By observing a nearby system just beginning its interaction and a more distant one in its final throes, we can piece together the entire narrative arc of cosmic violence and creation, understanding how these brief, furious chapters write the enduring story of the universe. Contemplating these cosmic forces inevitably leads us to a deeper, more personal line of inquiry. If the universe itself operates on a cycle where the most beautiful structures are born from violent encounters, what does that tell us about our own place within it? We are not separate observers of this grand drama, we are products of it. Every atom of oxygen in the air we breathe, every particle of iron in our blood, was forged in the heart of a massive star that lived and died violently long before our sun even ignited. Our very existence is a direct result of the same destructive and creative forces that shape tidal galaxies. This realization collapses the distance between the cosmic and the personal, placing us firmly within a continuum of transformation that spans billions of years. This cosmic perspective challenges a very human instinct to see destruction as a final, negative outcome. We witness a supernova and see a star's death, but the universe sees the dispersal of essential elements for new planets and life. We observe galaxies colliding and see chaos, but the cosmos sees the ignition of new suns and the birth of new worlds. The study of tidal galaxies invites us to adopt this broader, more resilient viewpoint. It encourages us to see endings not as absolute conclusions, but as necessary phases that clear the way for new beginnings. This isn't about minimizing loss or tragedy in our own lives, but about recognizing a fundamental pattern of renewal that is woven into the very fabric of reality, from the smallest ecosystem on Earth to the largest structures in the heavens. This pattern echoes profoundly throughout human experience and the natural world around us. Forests depend on periodic wildfires to clear out old growth and release nutrients that allow new seeds to germinate. Our own bodies constantly break down and rebuild cells, a process of microscopic destruction and creation that sustains our very lives. Innovation and progress in human societies often follow periods of great upheaval and change, where old systems are challenged to make way for the new. The universe, in its grandest and smallest expressions, seems to consistently favor this cycle of breakdown and rebirth. Recognizing this can foster a profound sense of resilience, our understanding that from periods of difficulty and disruption, new strength, adaptation, and beauty can indeed emerge. Ultimately, the lesson from Tidal Galaxies is one of profound connection and humility. It encourages a holistic view of existence where we are not isolated beings on a fragile rock, but an integral part of a dynamic, evolving, and incredibly robust universe. The same forces that gently hold the moon in orbit around our planet are the very ones that tear galaxies apart and ignite new stars. This knowledge doesn't make our personal challenges any smaller, but it can grant us a powerful sense of context and perspective. We are participants in a universe that is both terrifyingly violent and stunningly creative, and our ability to observe, understand, and reflect upon this magnificent process is perhaps one of the most beautiful and curious results of it all. Now, let's expand our view from the intimate dance of two galaxies to the grand ballroom of the cosmos itself, the immense galaxy cluster. These are the universe's most massive gravitationally bound structures, vast cities of hundreds or even thousands of galaxies, all swarming around a common center of gravity. It is within these dense, bustling metropolises that the story of tidal interactions escalates from a dramatic duet into a full-scale symphonic performance of cosmic violence and evolution. The forces we've been exploring don't just happen in isolation here. They become the dominant rhythm of life, shaping the fate of entire communities of galaxies in ways both beautiful and brutal. A perfect example of this is the Virgo cluster, the closest large cluster to our own local group, located about 54 million light-years away. It's a sprawling dominion of over 2,000 galaxies, all bound together by their mutual gravity and immersed in a searingly hot atmosphere of plasma known as the intracluster medium. In such a densely packed environment, galaxies don't simply drift past each other occasionally. They are in constant, close proximity. This makes gravitational encounters not rare, special events, but rather a fundamental and ongoing process. The tidal forces at work are not just between two partners, they are relentless and come from all directions. A galaxy moving through the cluster core experiences a continuous barrage of gravitational tugs from near neighbors and from the collective gravitational pull of the entire cluster's immense dark matter halo. This phenomenon is known as galaxy harassment, a term that perfectly captures the persistent, wearing down effect of these multiple, rapid-fire encounters. The consequences of living in such a violent neighborhood are profound and visible. The relentless tidal forces and the pressure from plowing through the hot intracluster gas have a transformative and often destructive effect on many cluster galaxies. Spiral galaxies, with their delicate disks and rich gas reservoirs, are particularly vulnerable. As they orbit through the cluster, the combined processes of harassment and gas stripping can efficiently tear away their star-forming material and disrupt their elegant structures. We see the evidence for this in the Virgo cluster itself, which contains a startling number of peculiar galaxies objects with distorted shapes, faint tidal streams, and missing gas. Many spirals here are converted into anemic spirals with weakly defined arms and little star-forming gas, or even into completely gas-free lenticular galaxies, which represent a sort of transitional form between a spiral and an elliptical. The cluster environment, through its intense and frequent tidal interactions, acts as a giant galactic factory, processing infalling spiral galaxies and reshaping them into smoother, redder, and more evolved systems. But the influence of these collective tidal forces extends far beyond altering individual galaxies. It fundamentally sculpts the architecture of the cluster itself and, by extension, the cosmic web. The same gravitational interactions that pull stars into streams within galaxies also operate on the scale of the entire cluster. Galaxies themselves can be pulled into vast, faint streams that trace their orbital paths around the cluster's center. Furthermore, the immense gravity of the cluster can tear entire dwarf galaxies apart completely, their stars dissolving into the cluster's halo to form a faint, diffuse background of intracluster light, a ghostly glow that is the final, dissolving evidence of countless past acts of cannibalism and destruction. This process helps build the giant, brightest cluster galaxies, behemoth ellipticals that sit at the very heart of clusters like Virgo, which have grown to their enormous size by consuming their smaller neighbors over billions of years. By studying the tidal features within clusters, astronomers can therefore map the history of the cluster's assembly, understanding how it grew by accreting and digesting smaller groups of galaxies over cosmic time. This expands our understanding of cosmic evolution from the scale of individual galactic encounters to the collective dynamics that govern the largest structures in the universe, revealing a hierarchy of violence where gravity reigns supreme at every scale. While gravity is the undeniable architect of these cosmic encounters, there is another, more subtle force weaving its way through the chaos, one that has long been overshadowed by its more powerful counterpart. This is the influence of magnetic fields. We often picture the space between stars as a perfect vacuum, an empty void, but it is in fact threaded through with incredibly weak magnetic fields, lines of invisible force that emanate from stars and permeate the vast clouds of interstellar gas. In a quiet galaxy, these fields are faint, their influence often negligible compared to the overwhelming power of gravity. However, when the violent turmoil of a galactic collision begins, these magnetic fields are not just passive spectators. They are caught up in the storm and dramatically amplified, becoming active players in the drama of creation. The process is one of incredible dynamism. As the tidal forces pull and stretch the galaxies, they don't just drag the gas and dust, they also pull on these magnetic field lines, stretching and winding them like infinitely elastic bands. Imagine taking a handful of loose, limp spaghetti and then twisting and pulling it tightly. The strands become aligned, organized, and under significant tension. This is precisely what happens to the magnetic fields within the tidal tails and compressed regions of colliding galaxies. Observations from radio telescopes, which are uniquely suited to detecting the synchrotron radiation emitted by electrons spiraling along magnetic field lines, have confirmed this phenomenon. They reveal that the magnetic fields in these areas are not only vastly stronger than in quiet regions, but are also highly ordered, their lines neatly aligned with the vast structures of the tidal tails themselves. This organization and amplification of magnetic fields has a direct and crucial impact on the star formation process we've been discussing. You might think that any force compressing gas would automatically help gravity form stars faster, but magnetism introduces a fascinating counterbalance. Magnetic fields exert a form of pressure, a resistance to being compressed. As the gravitational tides try to squeeze a cloud of gas to the point of collapse, the strengthened magnetic field within it pushes back, effectively providing extra support against gravity's pull. This magnetic pressure can slow down the collapse, making it a more controlled and regulated process. It can prevent a cloud from fragmenting too quickly or too chaotically, potentially leading to the formation of fewer, but more massive and stable star-forming cores. In this way, magnetism acts as a moderator in the stellar nursery, ensuring that the birth of stars isn't an entirely runaway explosion but a more managed event, influenced by more than just gravity alone. This adds a breathtaking layer of complexity to our understanding of these cosmic events. A galactic collision is not a simple story of gravity versus inertia. It is a collaborative and sometimes competitive interplay of multiple fundamental forces. Gravity initiates the dance, pulling the galaxies together and providing the primary compressive force. Hydrodynamics governs how the gases flow, shock, and mix together. And now we see that magnetism provides a subtle but pervasive structural influence, shaping the very way the gas collapses under gravity's relentless pull. It is a cosmic symphony where each force plays its own essential part, and the resulting stellar populations, the types, sizes, and distributions of the new stars, are the direct result of this intricate collaboration. The presence of these amplified magnetic fields, once an overlooked detail, is now understood to be a critical factor in determining the final outcome of the universe's most violent and creative performances. The ability to gaze not just into the deep past but into the far future of the cosmos is one of the most profound powers granted to us by the study of tidal galaxies. By carefully analyzing the gravitational scars of past collisions and applying the immutable laws of physics, astronomers have moved beyond simply reconstructing history. They can now forecast the destiny of galaxies with remarkable confidence. This predictive power transforms our understanding of the universe from a static picture album into a dynamic, evolving movie, where we can fast-forward billions of years to see the next acts of cosmic violence and creation unfold. This forecasting begins with precise measurement, using telescopes like the Gaia Space Observatory, which is meticulously mapping the positions and motions of billions of stars in our galaxy and beyond. Astronomers can calculate the trajectories of nearby galaxies with unprecedented accuracy. It's a celestial form of ballistics, tracing the path of an object through space by understanding its current velocity and direction. For our own Milky Way, this has allowed scientists to confirm its inevitable collision with the Andromeda galaxy. But the predictions go far beyond just our local neighborhood. By surveying vast volumes of the universe and employing sophisticated statistical models, cosmologists can create large-scale simulations that predict the rate of galactic interactions across cosmic time. They can analyze the gravitational pull of entire galaxy clusters and map the flows of galaxies along the cosmic web, identifying which systems are on converging paths and which are destined to drift apart forever, carried away by the accelerating expansion of the universe driven by dark energy. The value of this predictive power is immense, serving both pure science and profound inspiration. For scientists, these forecasts are crucial for testing our most fundamental theories of gravity and cosmology. If our predictions, based on Einstein's general relativity and the standard model of cosmology, consistently match what we eventually observe, it provides powerful validation that our understanding of the universe's operating system is correct. Conversely, if reality deviates from the prediction, it could point the way toward new physics, perhaps revealing secrets about the nature of dark matter or dark energy. It turns the future of the cosmos into the ultimate laboratory for testing our ideas. For all of us, these predictions inspire a deep and humbling sense of wonder. They place us within a grand, unfolding narrative that is far greater than our own fleeting existence. knowing that in 4 billion years our galaxy will undergo a magnificent transformation connects us to the future in a tangible way. It sparks the imagination to picture the night sky of a far future Earth, filled with the swirling light of a merging galaxy, and to contemplate the new stars and worlds that will be born from the chaos. This long-term perspective is a powerful antidote to short-sightedness, reminding us that change and renewal are the fundamental constants of the cosmos. The violence that shapes galaxies is not a destructive end, but an eternal engine of innovation, ensuring that the universe will continue to evolve, transform, and create new wonders long after our sun has faded. Perhaps one of the most remarkable aspects of these celestial collisions is their unique power to transcend the boundaries of pure science and reach directly into the public consciousness. The stunning, almost artistic imagery of galaxies like the antennae or the Tadpole, with their sweeping arcs and brilliant knots of blue stars, possesses an immediate and visceral impact. These are not faint, blurry smudges in a telescope eyepiece. They are cosmic masterpieces captured in exquisite detail by space observatories that tell a dramatic story of force and creation which anyone can appreciate on an emotional level, even before they understand the complex physics at play. This inherent beauty and narrative power makes tidal galaxies some of the most effective ambassadors for astronomy, serving as a perfect gateway to engage people of all ages and backgrounds with the wonders of the universe. In classrooms and museums around the world, these images become invaluable teaching tools. It is one thing to explain the abstract concept of gravitational tidal forces. It is quite another to show a student a side-by-side comparison of a serene spiral galaxy and the violently distorted Cartwheel galaxy, its perfect ring a direct and obvious consequence of a cosmic collision. The visual evidence makes the invisible force of gravity suddenly tangible and comprehensible. Educators can use these dramatic examples to illustrate a whole host of concepts, from Newton's laws of motion and universal gravitation to the life cycles of stars and the dynamic, ever-changing nature of the cosmos. A single image can spark 100 questions, turning a passive lesson into an active investigation and fostering the kind of curiosity that is the bedrock of scientific literacy. This public engagement extends far beyond formal education. The release of a new Hubble or James Webb image of an interacting galaxy is often a major media event, splashed across news websites and social media platforms, reaching millions of people who might never actively seek out scientific information. These shared moments of awe and wonder create a common ground, a point of connection between the often esoteric world of astrophysics and the daily lives of people everywhere. They remind us that we are part of a vast, dynamic, and astonishingly beautiful universe, fostering a sense of perspective and a collective appreciation for the pursuit of knowledge. In an era often dominated by short-term concerns, these glimpses into deep time and cosmic scale provide a humbling and inspiring counterpoint. Ultimately, this outreach is an investment in the future. A child who sees a poster of the mice galaxies on a classroom wall, or a teenager who watches a documentary detailing the future collision of the Milky Way and Andromeda, might feel that first spark of inspiration that leads to a lifelong passion. That spark could ignite the curiosity of the next great astronomer, the engineer who designs a future space telescope, or simply an informed citizen who supports scientific endeavor and thinks critically about the world. By captivating the imagination, tidal galaxies do more than just teach us about the universe's past. They help ensure that there will always be new generations of explorers ready to continue unraveling its mysteries, reminding us that the story of discovery is one we are all a part of. While we often marvel at the grand, galaxy-spanning ballet of tidal forces, This profound physical process is not confined to these epic scales. The same gravitational principles that pull entire galaxies into sweeping arcs of stars are also at work right here in our own solar system, operating on a far more intimate but equally fascinating level. This universality is a stunning demonstration of gravity's role as the master sculptor of the universe, a force that shapes reality from the smallest moonlet to the largest galaxy cluster with the same unwavering set of physical laws. Consider the humble ocean tide here on Earth. The rhythmic rise and fall of the sea is a direct and daily experience of a tidal interaction. It is caused primarily by the gravitational pull of our moon. The moon's gravity doesn't just pull on the Earth as a whole, it pulls more strongly on the side of our planet that is facing the moon. This differential force stretches the Earth slightly, but because the ocean is fluid, it responds more dramatically, bulging out towards the moon. A second bulge occurs on the opposite side of the planet, created by the centrifugal force of the Earth-Moon system's rotation around its common center of mass. As the Earth rotates, different coastlines pass through these bulges, resulting in the high and low tides we observe. The Sun also plays a role, with its gravity reinforcing the Moon's effect during full and new moons to create especially high spring tides, and working against it during quarter moons to produce weaker neap tides. This is a tidal process in action, a gentle, continuous deformation driven by gravity. But the effects of these planetary tides extend far beyond shaping our coastlines. They can be a powerful engine of geological and even potential biological activity elsewhere in our solar system. The most spectacular example is Io, the innermost of Jupiter's 4 large Galilean moons. Io is caught in a perpetual gravitational tug-of-war between the massive planet Jupiter and its sister moons, Europa and Ganymede. This constant, conflicting pull generates immense tidal friction within Io's interior, heating its core to the point that it has become the most volcanically active body in the entire solar system. Its surface is a constantly changing mosaic of hundreds of active volcanoes, spewing plumes of sulfur and lava high into its thin atmosphere. The tidal forces acting upon Io have turned it inside out, making it a fiery inferno. This demonstrates that tidal heating is not a mild phenomenon. It can be the dominant factor in a world's evolution, providing an internal heat source that has nothing to do with the distant sun. This concept of tidal heating unlocks one of the most exciting frontiers in astrobiology, the search for life beyond Earth. Scientists now believe that liquid water, that essential ingredient for life as we know it, may exist not on the surfaces of distant exoplanets, but in vast subsurface oceans hidden beneath the icy shells of moons right here in our own solar system. Europa, another moon of Jupiter, and Enceladus, a small moon of Saturn, are both prime candidates. Both are too far from the Sun to be warmed by its rays. Instead, their liquid interiors are likely maintained by the same kind of tidal heating that torments Io. As these moons orbit their giant planets in slightly elliptical paths, the varying gravitational pull flexes and stretches their cores, generating enough internal heat to keep massive global oceans in a liquid state despite the frozen, cratered surfaces above. The dramatic water geysers observed erupting from Enceladus's south pole are direct evidence of this internal, tidally powered activity, venting samples of that subsurface ocean into space. This reveals that tidal forces can create and maintain habitable environments in the cold, dark reaches of a solar system, vastly expanding the number of potential abodes for life in the cosmos. This thread of connectivity, from the ocean tides on our world to the volcanic fury of Io and the hidden oceans of Europa, weaves a consistent story. It shows that the awesome phenomena we witness on a galactic scale are simply magnified versions of the same physics that operate in our celestial backyard. The tidal tails of the mice galaxies are, in their essence, the same as the tidal bulges in Earth's oceans. Both are the result of a differential gravitational force stretching a celestial body. One is on a scale of hundreds of thousands of light years, the other on a scale of thousands of miles, but the underlying principle is identical. This universality underscores the beautiful simplicity and power of gravity. It is a force without preference, acting consistently on all mass, everywhere, linking the intimate pull of our moon to the majestic, slow-motion collisions of island universes, and revealing a cosmos deeply interconnected by the same fundamental rules. Yet for all the breathtaking images and profound insights we've explored, there remains a fundamental and humbling challenge at the very heart of this field of study. The spectacular tidal tails and faint streams that tell the story of galactic collisions are among the most elusive features in the entire night sky to observe. Their ethereal beauty in a Hubble image belies a simple, stark reality. They are incredibly faint, their light diluted across vast expanses of space, making them notoriously difficult to detect and even harder to study in detail. This inherent faintness pushes our technology to its absolute limits and forces astronomers to become masters of innovation, constantly devising new ways to see the unseeable. The core of the problem lies in a concept known as surface brightness. Unlike a star, which is a brilliant point of light, the light from a tidal stream is spread out over a huge area. Imagine the difference between a single, powerful lighthouse beacon and the gentle, diffuse glow of a city seen from an airplane at night. The lighthouse might be visible from much farther away, even though the total light from the entire city is vastly greater. A tidal stream is like that city. Its total light can be significant, but because it is smeared across hundreds of thousands of light years, its surface brightness, or brightness per unit of area, is extremely low. This makes it incredibly vulnerable to being washed out by any other source of light, whether it's the natural glow of our own atmosphere, the brilliance of the parent galaxy's core, or even stray light from our own cities here on Earth. Overcoming this challenge demands the largest telescopes humanity can build, instruments with massive light-collecting mirrors that can act as cosmic buckets, gathering every precious photon over many hours or even multiple nights of continuous observation. This process, known as taking a long exposure, is like using a very slow shutter speed on a camera in a dark room. It allows the faint signal to gradually build up until it becomes visible. But even this is not enough. The most groundbreaking work often requires getting above Earth's atmosphere altogether. The air we breathe, which shimmeringly distorts starlight and glows faintly itself, is the enemy of low-surface brightness astronomy. Space-based telescopes like Hubble and now James Webb provide a crystal-clear view, free from this atmospheric interference, which is why they have delivered the most iconic and detailed portraits of interacting galaxies. However, the technological innovation doesn't stop at just building bigger telescopes or launching them into space. A huge part of the battle is fought in the realm of data analysis and processing. The raw data from these long exposures is often filled with artifacts, noise, and the overwhelming glare from the bright central galaxies. Astronomers must use sophisticated software algorithms to carefully subtract that brilliant core light, a painstaking process akin to trying to hear a whisper in a roaring stadium by digitally removing the roar. They also have to contend with other foreground and background objects, like faint Milky Way stars or distant galaxies, that can be mistaken for parts of a tidal stream. Confirming a faint feature is truly a tidal stream, and not just a chance alignment, requires statistical rigor and cross-checking observations across different wavelengths of light. This relentless push to see fainter and fainter detail is far more than a technical exercise. It is the driving force that expands the frontiers of our knowledge. Every time a new, larger telescope like the forthcoming Vera C. Rubin Observatory comes online or a new data processing technique is perfected, it's like getting a new prescription for glasses. We suddenly see a universe that is far richer and more dynamic than we ever imagined. Faint streams that were once mere hints in a photograph are revealed in their full, intricate glory, telling a more complete story of a galaxy's past encounters. We discover that tidal features are not rare oddities but are in fact ubiquitous, suggesting that galactic interactions are a common and fundamental part of nearly every large galaxy's history. This ongoing struggle against faintness, this drive to push our observational capabilities to the brink, is what continuously rewrites our textbooks and deepens our understanding of the violent, creative, and beautifully interconnected cosmos we call home. To truly appreciate the significance of tidal galaxies, we must journey back in time to the very dawn of the cosmos, to an era known as the Cosmic Noon. This period, a few billion years after the Big Bang, was a far more chaotic and crowded place than the universe we inhabit today. Because the universe was significantly smaller and denser, galaxies were packed much closer together, making close encounters and dramatic collisions not just occasional events, but the standard mode of existence. This relentless, high-speed traffic meant that the beautiful, serene spiral galaxies we often picture were a rarity. Instead, the early universe was a tumultuous construction zone, dominated by irregular, clumpy, and violently interacting proto-galaxies. In this primordial environment, the tidal forces we see shaping modern galaxies were not merely influential. They were the fundamental architects, the primary engines responsible for building the first large galactic structures from the raw materials of the young cosmos. This presents a fascinating challenge for astronomers. How can we possibly study an era so distant and ancient? The light from that time has been traveling for over 10 billion years to reach us, making direct observation incredibly difficult. The key lies in a principle fundamental to all astronomy. The universe is our history book, and distance is a time machine. When we train our most powerful telescopes on extremely distant galaxies, we are not just looking across vast stretches of space. We are peering back into deep time, seeing those galaxies not as they are today, but as they were when their light first began its journey to Earth. However, these ultra-distant objects appear incredibly faint and small, often as little more than fuzzy red blobs. It is immensely challenging to discern the fine details of their structure or identify the telltale signs of tidal interactions from such a great distance. This is where our nearby tidal galaxies become absolutely invaluable. They serve as our local cosmic laboratories, providing a detailed, up-close look at physical processes that were ubiquitous in the early universe. A system like the Antennae galaxies, which is a mere 45 million light-years away, is close enough for our telescopes to resolve in stunning detail. We can study its violent star formation, map its intricate tidal tails, and measure the velocities of its gas and stars. By developing a thorough, precise understanding of the physics at work in this nearby collision, we can create a robust template, a set of diagnostic rules that describe what a galaxy looks like when it is undergoing a major merger. We then take this template and apply it to those faint, distant blobs of light from the early universe. If their properties, their shapes, their colors, their rates of star formation, their light spectra, match the predictions of our models based on nearby collisions, we can confidently identify them as galaxies in the throes of their own violent, formative encounters. In this way, the careful study of a nearby galactic wreck allows us to act as cosmic detectives, reconstructing the crime scene of the early universe from the evidence we can gather locally. The implications of this are profound. It suggests that the majestic galaxies we see today, including our own Milky Way, were largely assembled through a hierarchical process of building and merging. The first galaxies to form were likely tiny, fragile things, no larger than the dwarf galaxies we see orbiting our own. Through a long history of successive collisions and cannibalism, these small building blocks were drawn together by gravity, merging to form larger and larger structures. Each major merger would have triggered a massive burst of star formation, rapidly enriching the galaxy with heavy elements and dramatically altering its shape. This violent, bottom-up method of construction was the dominant mode of galaxy growth for the first half of the universe's history. Therefore, when we gaze at a nearby tidal galaxy, we are not just looking at a singular event. We are witnessing a replay of the very processes that built the foundational structures of the cosmos itself, a living fossil from an age of violent creation that shaped everything we see around us. Yet, even as gravity pulls galaxies together in these spectacular collisions, another far more mysterious force is working on the largest scales of all, pushing them apart and fundamentally shaping the future of cosmic evolution. This force is dark energy, an enigmatic form of energy inherent to the fabric of space itself that is causing the expansion of the universe to accelerate. While gravity acts as a local sculptor, drawing matter together to build structures like galaxies and clusters, dark energy acts as a global influence, stretching the very space-time between those structures. This creates a fascinating and ongoing cosmic tug-of-war, where the destiny of galaxies is caught between the relentless pull of gravity and the pervasive push of dark expansion. The influence of dark energy on galactic encounters is profound, though it operates on timescales that dwarf human comprehension. To understand it, we must think about the future of the universe. As dark energy continues to accelerate the expansion of space, the vast distances between galaxy clusters will grow at an ever-increasing rate. Galaxies that are not already bound together by gravity in local groups will find themselves carried away from one another on this expanding spacetime, like raisins in a rising loaf of bread that is baking faster and faster. This means that for galaxies that have not yet begun a gravitational dance, the window of opportunity for a future collision is slowly closing. The universe is becoming a much more spacious place, and the era of frequent, large-scale galactic mergers is ultimately finite. This doesn't mean that all cosmic violence will cease immediately. Within gravitationally bound structures like our own local group, which contains the Milky Way, Andromeda, and about 60 other smaller galaxies all held together by their mutual attraction, the future is still one of interaction and merger. Dark energy's influence on these relatively small, bound systems is negligible. Gravity has already won that local battle. The eventual collision between the Milky Way and Andromeda is still firmly on the cosmic calendar. However, beyond these local islands, the story changes dramatically. Future galaxies forming in isolation will likely never interact with another major galaxy. They will evolve in solitude, their growth through cannibalism limited to absorbing only the tiny dwarf satellites that may already be orbiting them. Their story will be one of quiet, internal evolution rather than the dramatic, transformative fires of collision. This interplay introduces a crucial temporal dimension to the story of galactic evolution. The universe has a history, and that history has distinct chapters defined by the dominant forces at play. The early universe was a time of frequent and violent mergers, the prime era of tidal galaxy formation, as everything was much closer together. We are currently living in what astronomers often call the stelliferous era, the age of stars, which is still dominated by gravity within galaxies and clusters. But we are transitioning into a future that will be increasingly dominated by dark energy. This shifting balance of power means that the processes we study in today's universe, the magnificent collisions that trigger starbursts and reshape galaxies, are not eternal. They are a signature of a specific cosmic epoch. By studying the rate of galactic interactions across deep time, astronomers can actually trace the influence of dark energy and better understand its nature and strength. The changing frequency of cosmic violence is itself a key piece of evidence in one of the greatest mysteries in modern physics, linking the fate of galaxies to the ultimate fate of the entire cosmos. These celestial collisions, these grand dances of destruction and creation, have never been confined to the pages of astrophysics journals. Their profound beauty and symbolic power have echoed through human culture for centuries, long before we even understood their true nature. When we look at a tidal galaxy, we are not just seeing a physical process. We are witnessing a universal story, one that has always resonated with the deepest parts of the human experience, themes of transformation, conflict, renewal, and the eternal cycle where endings are inseparable from beginnings. This cultural connection often begins with the artists, those who translate the invisible forces of the cosmos into something we can feel. The swirling, ethereal forms of interacting galaxies have become a wellspring of inspiration for painters, digital artists, and sculptors. They see in these cosmic accidents a natural abstraction, a composition of light, color, and form that speaks to something beyond mere representation. An artist might use the image of the antennae galaxies not to create a scientifically accurate chart, but to evoke a sense of majestic turmoil and beautiful chaos. The sweeping arcs of tidal tales find their way into brushstrokes and digital renders, becoming metaphors for emotional upheaval, the pulling apart of the self, and the eventual reformation into something new and unexpected. This artistic interpretation does more than just create beautiful objects. It builds an emotional bridge, allowing us to connect with the cosmos on a visceral level, transforming cold astrophysics into a shared human experience. This resonance extends powerfully into the stories we tell ourselves, our myths and literature. The narrative of a galactic collision is a ready-made epic. It is a story of two mighty kingdoms, two distinct cultures, each with their own histories and populations of stars, meeting in a cataclysm that changes both forever. It is a tale of a great battle that ultimately leads to a new united kingdom, a phoenix rising from the ashes. Writers of science fiction have long grasped this potent symbolism. In countless novels and films, the collision of galaxies serves as a backdrop for stories about societal transformation, the clash of civilizations, or the literal end of one world and the painful birth of another. These narratives use the cosmic scale to explore deeply human questions about identity, resilience, and our place in a universe that is far from static. They remind us that the grand cycles we see in the heavens are reflected in our own lives, in the constant processes of personal growth, decay, and rebirth. Perhaps most importantly, this cultural dialogue is a two-way street. Just as science inspires art and public fascination can profoundly influence the direction of science itself. The breathtaking images released by space telescopes are not merely data. They are carefully processed and often colorized to highlight specific features, a process that itself requires an artistic eye to communicate scientific truth effectively. These images, which become cultural icons, generate public wonder and support. That widespread captivation helps secure funding for the next great telescope, inspires a new generation of students to pursue astronomy and fosters a general appreciation for fundamental research. The beautiful picture of a tidal galaxy is not the end result of science. It is often the very thing that draws people in to care about the complex physics behind it. In this way, the cultural impact of these discoveries fuels the scientific engine, creating a virtuous cycle where wonder leads to inquiry, and inquiry leads to even greater wonders. The story of tidal galaxies, therefore, is not complete when the physics is understood. It is only complete when that understanding sparks something in us, a painting, a poem, a moment of quiet reflection, weaving the cosmic into the tapestry of human culture and reminding us that we are not just observers of the universe, but conscious participants in its ongoing story of beauty and change. While our current telescopes have unveiled the breathtaking drama of galactic collisions, the next great leap in understanding is already underway, propelled by a new generation of observatories that will see the universe in ways we once thought impossible. At the forefront of this revolution is the James Webb Space Telescope, an instrument that is fundamentally changing the game. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is an infrared powerhouse. This is a critical distinction because the long, dusty tidal tails and the stellar nurseries buried within them are often shrouded in cosmic dust that blocks visible light. Webb's infrared eyes peer straight through that obscuring veil, revealing the hidden heart of the collision. It can detect the faint heat signatures of the very first stars beginning to ignite in a tidal tail, measure the chemical composition of the gas in these streams with exquisite precision, and even identify the building blocks of planetary systems around newborn stars in these chaotic environments. It's like moving from a silent black and white film to a full-color, high-definition movie with surround sound. The level of detail is simply transformative, allowing us to witness the process of creation within the violence with unprecedented clarity. But Webb is not working alone. Here on the ground, the Vera C. Rubin Observatory is preparing to undertake a mission of a completely different, yet equally revolutionary scale. While Webb focuses on deep, detailed studies of individual objects, Rubin will conduct a relentless, decade-long survey of the entire available sky. Its immense 3.2 billion pixel camera will capture the heavens night after night, not just once, but over and over again. This monumental project will create an unprecedented motion picture of the universe. For the study of tidal galaxies, this is a game changer. Rubin's relentless gaze will detect the incredibly faint, diffuse streams of stars that are the ghosts of past galactic encounters, features too large and too subtle for most telescopes to easily see. More importantly, by comparing images taken nights, weeks, and years apart, it will allow astronomers to actually measure the subtle, slow motions of stars within these tidal streams. For the first time, we won't just see the static aftermath of a collision. We will be able to chart the velocity and direction of the debris, providing a dynamic, three-dimensional map of the gravitational forces at work and offering a direct window into the distribution of the dark matter that is guiding the entire process. The synergy between these two giants will be where the real magic happens. Webb will act as the ultimate cosmic microscope, zooming in with incredible detail on the most interesting and peculiar objects that Rubin's Wide Field Survey discovers. Imagine Rubin scanning the sky and flagging a distant galaxy with a bizarre, faint wisp of light extending from it, a potential tidal feature from a collision we didn't know about. This coordinate is then immediately passed to Webb, which can turn its massive golden mirror towards it, dissecting its light to determine its age, composition, and history. This powerful partnership between Wide Field Survey and targeted deep observation will create a virtuous cycle of discovery, ensuring that no cosmic clue goes unnoticed. It will undoubtedly lead to the discovery of entirely new classes of tidal interactions, perhaps ones that challenge our current simulations and force us to rethink aspects of galactic physics. This is not the end of the journey, it is the beginning of a new chapter. The data from these observatories will feed the next generation of computer simulations, which will need to become even more complex and sophisticated to account for the new layers of detail we observe. We will move from simply replicating the shapes of tidal tails to accurately modeling the intricate dance of magnetic fields within them, the precise rates of star formation, and the chemical enrichment of the gas. These future tools promise to do more than just confirm our existing theories. They will undoubtedly uncover new mysteries we haven't even thought to ask about yet, ensuring that our understanding of cosmic violence and creation remains a vibrant and ever-evolving story. It's a humbling thought that some of the most profound truths about our universe have been uncovered not by rigid design, but by pure, unexpected chance. The history of astronomy is filled with these wonderful accidents, moments where a scientist looking for one thing stumbled upon something entirely different and far more revolutionary. This element of serendipity is not a flaw in the scientific process. It is one of its most vital and beautiful components. It reminds us that for all our advanced technology and sophisticated theories, the cosmos still has the power to surprise us, often leading to discoveries that reshape our entire understanding of reality. Consider the iconic story of the discovery of the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were simply trying to calibrate a supremely sensitive horn antenna for satellite communication experiments. They were plagued by a persistent, faint static that seemed to come from every direction in the sky. They meticulously cleaned out pigeon droppings from the antenna, checked every electrical connection, and eliminated every possible source of interference, yet the annoying hiss remained. What they had initially dismissed as an equipment nuisance turned out to be the most important cosmological discovery of the 20th century, the cooled remnant of the universe's fiery birth. They weren't looking for it, they were just thorough, curious, and open-minded enough to recognize that their problem was actually a message from the dawn of time. This tradition of accidental discovery is deeply woven into the study of tidal galaxies as well. Many of the most spectacular and informative tidal streams and tails were not the primary targets of observation. They were found by astronomers who were conducting broad surveys of the sky, perhaps cataloging stars within our own galaxy or searching for distant quasars. In the photographic plates or, later, in the digital data from these wide-field surveys, they would notice faint, unexpected smudges, arcs, or wisps of light extending from otherwise normal-looking galaxies. A less curious mind might have dismissed these features as imperfections in the image or scattered light from a bright star. But because these astronomers possessed a keen eye and a willingness to be sidetracked, they followed the clue. What they thought was a minor anomaly turned out to be the brilliant, sprawling evidence of a galactic collision, a fossil record of a gravitational encounter that occurred billions of years ago. This underscores a critical lesson about how science truly progresses. While we often picture it as a linear, logical march from hypothesis to experiment to conclusion, the reality is far messier and more exciting. The most groundbreaking advances often come from the periphery, from the unplanned observation, the failed experiment, or the curious anomaly that doesn't fit the established model. It is the scientists' cultivated sense of wonder and their refusal to ignore the unexpected that transforms a mistake into a milestone. This is why fostering curiosity-driven, basic research is so essential. It creates the fertile ground in which these chance discoveries can take root and grow. When we allow astronomers to simply look at the sky with the best tools available, without demanding a specific, immediate result, we are effectively investing in serendipity. We are giving the universe an opportunity to show us something we didn't even know we should be looking for, trusting that the pursuit of pure knowledge will, in its own time, yield the deepest rewards. For centuries, the grand diversity of galaxies in the universe presented a magnificent puzzle. We had majestic spirals, smooth ellipticals, and a whole zoo of irregular shapes, but no single story that could explain how they all came to be. It was as if we were looking at a forest containing every type of tree saplings, ancient oaks, and twisted, gnarled forms, without understanding the soil, the weather, and the life cycles that connected them all. The study of tidal galaxies has provided the crucial missing chapters in that story, revealing that the key to understanding this diversity is not to see each galaxy in isolation, but to see it as a product of its violent and creative interactions. We are now weaving these individual threads of discovery into a single, unified tapestry, a comprehensive theory of galaxy evolution that finally accounts for both the beautiful order and the beautiful chaos we observe. This holistic approach is built on a powerful synthesis of insights. It starts with the fundamental role of gravity, the great architect that draws galaxies together and orchestrates their collisions. From there, we integrate the transformative power of these encounters, how tidal forces trigger immense waves of star formation, how they can completely reshape a galaxy's morphology from a spiral into an elliptical, and how they lead to galactic cannibalism, where larger galaxies grow by consuming smaller ones. We then layer in the influence of the invisible world, how these interactions allow us to map the mysterious dark matter halos that guide the process, and how they can awaken the supermassive black holes at galactic centers, whose powerful feedback can both quench and ignite new creation. Finally, we account for the chemical enrichment, the dispersal of heavy elements that provides the raw material for new planets and potential life. Each of these processes was once studied in its own separate silo. The new unified theory recognizes they are all interconnected parts of a single dynamic narrative. The ultimate testing ground for this grand synthesis is not in any single observation, but in the incredible power of modern computer simulations. These virtual universes, running on the world's most powerful supercomputers, are where the theory either stands firm or falls apart. Astronomers input all the known laws of physics, gravity, hydrodynamics, thermodynamics, and set the initial conditions to match the universe shortly after the Big Bang, a nearly smooth soup of dark matter and gas. They then press play and watch as the simulation runs forward over billions of years of cosmic history. The true test is whether this virtual universe, governed solely by these rules, spontaneously generates the rich diversity of galaxies we see today, complete with the correct proportions of spirals, ellipticals, and, crucially, the tidal features and merger remnants that tell the story of their violent past. The success of these simulations has been nothing short of breathtaking. They show small, primordial clumps of dark matter and gas merging hierarchically, building up larger and larger structures. They show spiral galaxies forming their delicate disks during periods of quiet accretion, only to have those disks be shredded and randomized during major mergers, transforming them into featureless ellipticals. The simulations accurately reproduce the spectacular tidal tails, the bursts of star formation, and the growth of supermassive black holes that we observe in real systems like the antennae galaxies. When the virtual universe emerging from the computer screen so perfectly mirrors the real one outside our telescopes, it gives us profound confidence that our unified theory is on the right track. We are not just cataloging phenomena, we are deciphering the underlying operating system of the cosmos. This journey towards a unified understanding does more than just satisfy scientific curiosity. It fundamentally changes our perspective on the cosmos and our place within it. It reveals a universe that is profoundly dynamic and interconnected, where a galaxy's present form is a living record of its past interactions. Our own Milky Way is not a static island universe but a work in progress, its current spiral structure and satellite system all testament to a long history of cannibalizing smaller galaxies. And its future, a merger with Andromeda, is not a freak accident but part of the standard life cycle for galaxies like our own. This theory binds all galaxies together into a single family tree, with gravity as the driving force behind a never-ending story of construction, destruction, and rebirth. It is a story that began with the faintest ripples in the early universe and continues to unfold today, with every galactic collision adding a new verse to the epic poem of cosmic evolution. And so, the story of Tidal Galaxies brings us to a profound and humbling conclusion, one that forever changes how we see our place in the cosmos. These magnificent collisions teach us a fundamental truth about the universe, that violence and creation are not opposites, but are instead two inseparable faces of the same cosmic coin. Every act of destruction we witness on these grand scales is simultaneously an act of renewal, a necessary step in the endless cycle of birth, death, and rebirth that has shaped everything from the smallest star to the largest galaxy. It is a cycle that operates on timescales we can scarcely comprehend, yet its principles echo throughout the natural world and even in our own lives, reminding us that endings are often just disguised beginnings. This grand perspective invites us to see the universe not as a static, frozen museum exhibit, but as a dynamic, living, and deeply interconnected system. The same gravitational forces that tear a galaxy apart also compress the gas that ignites new suns. The same collision that disrupts ancient planetary systems also sows the seeds for new worlds in enriched stellar nurseries. The supermassive black hole awakened by the influx of gas can both quench star formation and, through its powerful outflows, trigger it elsewhere. There is no clear line between chaos and order. They are partners in an eternal dance, each giving meaning to the other. This interconnectedness extends to us as well, for we are literally made from the elements forged in the hearts of stars that lived and died in these very collisions. We are not just observers of this cosmic story, we are products of it, living testaments to the universe's creative power. As our journey through the mysteries of space continues, let the lessons of Tidal Galaxies inspire not just awe, but a deeper curiosity about the universe and our role within it. Let them remind us that the pursuit of knowledge is a never-ending adventure, filled with surprises and wonders that challenge our understanding and expand our horizons. The next time you look up at the night sky, remember that you are gazing upon a cosmos in constant motion, a grand tapestry being woven and rewoven by forces of unimaginable power and beauty. We thank you for joining us on this exploration. We would love to hear your thoughts and questions in the comments below, and if you want to join us for more journeys to the frontiers of knowledge, be sure to subscribe. Until next time, keep